either I drive it home and come back, or...
Hello, everyone. Welcome back to the RI seminar. It is my great pleasure today to introduce Professor Nikolay Atanasov. Professor Nikolay is from University of California, San Diego. He is in the Department of Electrical and Computer Engineering. Before he was a professor, he did his master's and PhD, also in electrical and systems engineering from University of Pennsylvania. And very broadly, Nikolay researches robotics, controls, machine learning. That's probably what we're going to be seeing today, with a strong emphasis on active perception problems for autonomous mobile robots. And so hopefully we're going to see what those foundations and frontiers look like today. Nikolay has a bunch of awards, including things like Best Conference Paper at ICRA, NSF Career Award, IEEE Ross Early Academic Career Award, and so on and so forth. But with all of that said, let's talk about the research. Thank you so much for showing up.
Thank you very much. Thank you for the kind introduction, and thank you for being here. I'm very excited to tell you a bit about the research in my lab, and I'm going to speak without a microphone. If you don't hear me well, please let me know. I'm happy to put it on. So let's jump into it. So my lab is called the Existential Robotics Lab, or ERL for short. And we work on problems like simultaneous localization and mapping, where we build maps that involve geometry and semantics. I'll say a lot more about this, but just a quick overview. We're interested in the active perception problem, where robots want to explore the space on their own and build a map autonomously. We look at multi-robot coordination. So if I have ground and aerial robots, how do we do things collaboratively, localize, map, motion plan, and do safe control? We've recently started working more on manipulation. We have a few arms now, and we've looked at reinforcement learning as well. We have a good number of work on control theory as well. We look at stability and safety problems, how to make sure you stay safe in the presence of dynamic and even adversarial obstacles. And more traditionally, we've also looked at motion planning problems, like if you have a aerial robot, for example, how do you plan trajectories that are safe, take your dynamics into account, and so on. So we've seen, a bit of motivation of what I'll talk about. So robots have been really impactful in kind of these controlled factory settings where they assemble cars or do kind of warehouse automation and so on. And to me, one of the big frontiers for robotics is to transition this to these more unstructured environments like autonomous driving. You don't have a good map in advance, or I don't think you should assume that, or kind of lab work or navigation in campus-like environments where things are a lot more unpredictable. So I think a very important thing to enable this kind of transfer to unstructured environments is mapping or environment understanding. And I think traditionally kind of we've seen a lot of progress in SLAM, but still a lot of the existing SLAM is very geometry oriented, obstacle avoidance oriented. So I think an important aspect is to think about maps that incorporate additional information, like capturing semantics, identifying objects and maybe object shapes or object poses and things like that. So today I'll talk about particular map representations, and then I'll show you how they can be useful for robot autonomy in unstructured environments. Okay, so let's jump into mapping. So I'm assuming we have as an input streaming sensor observations. The most common ones we have are RGB or some sort of depth or LiDAR, and maybe semantic segmentation. Nowadays we can segment images into objects. And the objective is to build a model, something that captures geometry and semantics, and it's preferably a continuous model, so we can do things like collision checking, motion planning, visibility prediction, and things like that. Okay, so let's see what are some common representations. So one that I assume many people are familiar with is just an occupancy map. So we have a function which is, let's say, 0 in free space and 1 in occupied space. And traditionally, we discretize space, and we just try to estimate this function. More recently, we've seen other formulations for dense representations. So one other very popular one is a signed distance function, So this is a step up from the occupancy function in that it gives you the distance to the nearest surface. Typically, you have it negative if you're inside an obstacle or an object, and positive outside. So O here is like my obstacle set, and this is a visualization of what assigned distance might be like. If you're close, you have higher values, which are red here, and if you're further away, you have bluish colors, which mean further away. And there are other models, something like a nerf, for example. We can look at it in this same point of view. Our inputs are position and viewing direction. So in a nerf, we have, in addition to the 3D coordinate, which I call P here, which is kind of the same as X up there, as well as a viewing direction, usually a unit vector in what direction you're looking at. And your output is some is either color or volume density along the ray. Okay, so let's look at how to, so the job of mapping is essentially to estimate these kind of functions. I have sensor observations, and I'm trying to approximate one of these functions. Okay, so let's start simple. So one very simple idea is to extend the occupancy function I mentioned to capture categories. So instead of a binary function, we can try to do classification. So we can have multiple classes. So let's say we have a depth image on the right and a semantic segmentation here as an input. Equivalently, we can think of this as a segmented point cloud. So I have a point cloud in which every point has some category assigned to it. And our objective is to build this kind of grid-like map in which every voxel has a vector of probabilities of the different classes. So instead of, again, in the binary case, you just have two possibilities, right? Either free or occupied. And here, now we can think of a whole vector in which we have different class probabilities. So let's think about this problem briefly. I think it's relatively simple, but just to mention a couple of things. So let's model each of our voxels as a random variable. So I'm going to call it mi, so the ith cell of the map. And it belongs from, it has a value from 0 to k. So if I have k different possible classes, and typically I'll have observations, as we said, this kind of colored point cloud. Let's call that z. And I have some observation model. Let's call it pz given mi. The typical approach in mapping is to do some Bayesian formulation. So you can write Bayes rule down. So for example, I have the likelihood that this ith cell is of class k, condition of on the observation from Bayes rule is the observation likelihood times the prior, and there's some normalization factor. And this is pretty simple to implement, except that computing this normalization factor is typically hard, and you want to avoid doing this as well. But one thing that's really nice in binary or multi-class classification is that you can actually avoid computing this. So I'll mention how. So if you have, let's write Bayes rule again, but for a different class. So I wrote it for class K. I can write the same for another class, let's say the 0 class. And so exactly the same thing. The main observation is that the normalization factor is the same, regardless of which class you write Bayes rule for. So this gives the idea that if you find the ratio of those two things, you will cancel the normalization factor. So this is called odds. So if you compute the odds of a binary or a multi-class variable, you don't need to compute normalization, which is pretty nice. And we also take logs, so you might have heard of log odds. The only reason to take log is just to make numerical things a little nicer. You have addition instead of products. So essentially, your Bayes rule now in this log odds formulation becomes the log of the ratio of probability of class k over 0 times the log of some observation model, which we typically parameterize or estimate or have. And this is the prior. So writing this in a simpler way, I have some vector of log odds for the different classes. And I have a vector of log odds given by the observation model. And I just add them together, and this gives me the posterior log odds. So updating the log odds actually becomes a pretty simple operation where I'm just adding this log odds model to the prior vector of log odds. And again, the h thing here is the log of the ratios of the different classes. You can do this for every cell, and we know that kind of voxel representations don't scale very well. So in practice, we also do some adaptive data structures like an octree or a hash map to make sure that this scales better. So for example, in the case of an octree, you can think about unifying classes that have similar probabilities into bigger octants to represent space a bit more efficiently. So there are more details, but this is the main idea. So I want to show you kind of what this looks like. So we've implemented this on a small race car-like robot. It has an NVIDIA Jetson type GPU on there, and we're doing ray tracing to update the octree, and we have the semantics. So on the left, you see semantic segmentation and the RGB, and we're updating the logouts of this map, and we can kind of map things like wall, window, ground, furniture, ceiling, and so on. Just very briefly, I'll mention we also have a multi-robot formulation of this. I'm not going to talk much about multi-robot stuff in this talk, but I'll just for completeness, I'll mention. You can think about now having multiple robots and a graph which specifies the communication between them. So every robot is a node, and the edges are kind of which robots can talk to each other and which ones cannot. So let's say we have this graph, V and G. Each robot maintains a variable. So in our case, this will be this octree that represents the map. And we have a constraint that the robots need to agree on their variables, meaning they want to have a common map that everyone agrees with. So we formulate this as a optimization problem in which we're minimizing some sum of local objectives. So each objective is, let's say, the log likelihood of the observations at each robot, subject to a constraint that the distance in the variables, the maps, is 0. So we want to ensure that the robots agree on this. So we have a distributed optimization algorithm for this. Again, I'm just mentioning this quickly. If anyone is interested, I'll discuss this more offline later on. But our algorithm essentially consists of 2 steps. You take a gradient step in the cost function, followed by a gradient step in the constraint. You'll notice that the constraint has to be 0. So essentially, if you minimize the constraint as well, you're approaching 0. And we prove that this kind of alternating gradient in the cost, gradient in the constraint, converges. And more importantly, you get a distributed algorithm. You only have the local objective at each robot. And if you take the gradient of this, you end up talking only with your neighbors. So we can implement that same semantic octree mapping algorithm in a distributed way. So let me show you what this looks like. So this is an experiment with 2 UAVs, 2 quadrouters. Again, we're running semantic segmentation, and we're updating the octree map at each robot. But now the robots are also communicating with each other and exchanging this map information. So this work is open source, both the single robot and the multi-robot version. It's called ROAM. It stands for Riemannian Optimization for Active Mapping, which you can check out if you're interested. There are more details I didn't mention. There's the active part. We also plan trajectories to explore and minimize uncertainty. But in this talk, I want to talk more about the representations. So this one was kind of a relatively simple one, right? We have voxels and we have categories. I want to go back into these distance-based representations and show you that they can be pretty useful. So let's consider now the sign distance function instead. We said the main difference was that instead of 0 and 1, I have some negative or positive distance to the obstacle I'm observing. So we can think of this as a learning problem. I can generate a training set of pairs where the observation is, let's say, position, and the measurement is the distance to the surface. And then the goal is to train a regression model that estimates the sign distance function. Let's give a little more details. So in practice, we get measurements something like this. We have some depth camera or a LiDAR sensor, which hits our obstacle at these red points over here. And to generate our data set, we typically pick some points around the place where we hit the environment. And for each of these green points, we measure the distance to the surface. So I can, for example, connect the red points here with lines. This is kind of my local estimate of the surface, and measure the distance from the green points to the surface to get some sort of a distance measurement. So I can construct a data set this way of xi's are the green points and yi's are their distance from the observed surface. So now the problem of estimating sign distance becomes pretty much a machine learning problem, right? I have the data set of distance measurements, and I'm interested in estimating the function f. And we can approach this with any regression model we want. So we can use a Gaussian process, or we can use a neural network. And I'll choose neural networks here and give you more details on how we can implement something like this. So the early approaches for neural sign distance function estimation just use the single MLP. So you treat your whole environment as a single MLP. And as you get more and more of these distance measurements, you update the MLP model to predict the distance. For example, ISDF is one of the early works that did that. And the nice result is you get a continuous function and fills in holes of places you haven't observed. But using a single MLP starts to run into problems. If your environment is large, you start to miss parts. You start to forget parts. More recent approaches in this SDF estimation use more complicated data structures. So for example, instead of having a single MLP, we start to think about having different features in the environment, which an MLP can decode again into a sign distance prediction. But those features are now organized in some fancier ways. For example, nicer SLAM has a structure where you have several levels of resolution, and at different levels you have like a field of features which you decode with the MLP. And MIPS fusion is another example which uses submaps, maybe motivated by earlier work in SLAM. So you kind of have an MLP per submap, and you have many of these submaps, so you need to think about how to align them. So this leads to much higher fidelity 3D reconstruction, but it's typically quite expensive, especially as you start to get into larger environments. How do you do this online, and how do you make sure you get good estimates? So we decided to look at this problem and focus on how to do this efficiently while being able to get good reconstruction. So our approach is called MISO. It stands for Multi-Resolution Submap Optimization. And it's a continuous and differentiable sign distance function representation. And we have two interesting ideas, or two contributions. One is that we use multi-resolution features. So essentially, we have coarser features to get like a rough estimate of what the environment looks like, and then finer level features. I guess our design can handle multiple levels, but in the experiments, I'll show you just two levels. We have coarse and fine, but you can have more in theory. And second, we also have this submap idea that I mentioned earlier. And the main question here is kind of how do you fuse, or how do you align the submaps to keep that consistent? OK, so let's talk about the MISO representation. So we think of the environment organized into keyframes. So in each region, I have a submap. And in the submap, I have a multi-resolution feature grid. What this means is I have a grid of features, but several of these grids at different resolution. And to decode this back to SDF, I do something like this. I concatenate features from the different levels of the grid. So L here stands for the level of the grid. I concatenate those features, and I pass them through a decoder, which gives me back a prediction of the sign distance function. If x, the query point, is somewhere in continuous space, you typically have some interpolation where you infer what the feature is at that continuous location. You do this interpolation at all the feature grid levels. You concatenate everything into a huge feature, and you pass through your decoder. So what this looks like is kind of we have the submap. We have these two feature grids. We have the coarse and the fine resolution here. These are the two different levels. If I have a query point x here, it's typically not exactly on the grid. So we do some interpolation process to estimate the coarse level feature here and the fine level feature here. We concatenate them together into one big feature vector. And we pass this through a decoder, which is typically pre-trained in order to make sure that we can operate in real time. And we predict SDF from this. OK, so this is the proposed design. So the objective is, two questions. Does this work well? And two, how do we accelerate the training of such a model? Again, I mentioned we pre-train the decoder and we freeze that. That's great. But still, the features are kind of high dimensional. How do we make sure we can optimize these efficiently? OK, so a little more on what the optimization looks like. We can form a SLAM problem now in which we have two variables. One are the features of the different levels in this grid. Like collectively, I call them this capital F, as well as the poses of the camera. So as the camera is moving around, or the robot is moving around, we have these robot poses. So we typically have some cost function here, which measures whether our predicted SDF is similar to the measured one. Plus, we have some regularization on the poses. I don't think this term is very important. You can ignore it. The main one we care about is some SDF reconstruction cost, in which kind of features, query locations are mapped to the local frame by the robot pose. And given the features, we reconstruct SDF, and we measure with respect to the sensor measurements whether this is accurate or not. OK, so how do we achieve faster optimization with this? So our intuition is that the coarse grid should somehow inform the fine grid. So if I first get a coarse, we want to do something like first get a coarse description of the environment and then fill in the details after. So how do we use that, right? So how do we use this intuition? So if we assume that everything is linear, actually there's some nice intuition. So if our, going back here, this cost and the decoder and everything, let's say the cost function was entirely linear. If I fix the features in the higher, in the coarser grid, and I ask what are the optimal features in the finer grid, if we have a completely linear problem, we know that the solution will look something like this. So we'll have some Jacobian here. We have the pseudo-inverse. This comes from the normal equations. So the main observation is that the optimal fine level feature, given the coarse level feature, is actually a linear function of the residuals. So the residual is kind of the error in this cost. So that's the main takeaway, right? The function which computes the optimal value of the fine level feature is actually a linear function of the residuals in the coarse level features. So this if the problem is linear. Okay, if the problem is not linear, we can try to use nonlinear functions. But the main idea is that we should be using the measurement residuals to inform what the features should be. Okay, so in the general case, our main idea then is to learn an encoder which is hierarchical. So for each level of our grid, we use a different encoder which predicts the features. So starting initially with a point cloud measurement with distances in the beginning, as I mentioned, we construct an encoder which takes the residuals as an input from the data set and predicts what the feature should be. So this gives us essentially a smart initialization for that coarse level optimization. We carry out the coarse level optimization, and we recompute residuals after the coarse level optimization. We have new residuals. We use a second encoder to predict what the fine level feature should be. Again, it's kind of a smart initialization for the fine level, and then we solve the problem. So the main idea here is that if we initialize our optimization problem in a good way, there's very few iterations we need to do online, and we can pre-train those encoders and freeze them just like for the decoder. So we can actually do a lot of the computation in advance, and then online we just need prediction from the encoder, a few iterations of optimization, and that's it. So the thing we do online is a lot less. So let's visualize what this looks like. So this is, for example, at the coarse level. This is a 2D slice of this mesh here on the right. This is what the residuals might look like. Here I'm showing two because we have you can have multiple cost functions. If you've ever worked with SDF, sometimes you have error in the distance, but you might also have things like the gradient has to be equal to, the norm of the gradient has to be equal to 1. That's called the Autonomy equation. So you might have additional cost functions there. If you will ignore the second one, we just have the residuals here based on the distances. We have the encoder. From the coarse level optimization, we get some prediction like this. Then from the coarse prediction, we can get new residuals for the fine features. We have an encoder again, and this gives us fine level initialization. And after we optimize everything, we get a reconstruction that looks something like this. So we compared this kind of hierarchical feature optimization to a few other methods. So we have ISDF was the one that was using a single MLP, and then neural points is inspired by this pin slum paper by Cyril Staknis' group, which uses kind of an unorganized point cloud of features to reconstruct SDF. So these are some qualitative results on ScanNet, and we have some numerical results. So we can get pretty good accuracy. So we're even able to improve on the accuracy, but the main point is that the time is significantly shorter. Just showing, oh yeah, and then one more problem. So what I described so far is kind of a local optimization. We're building a map, but over time, typically in robotics, we have odometry, which drifts. So we might start to get problems like this. So if our odometry, the red curve here, is wrong, our local maps might be good, but the global map might look not so great. So our second thing we did is to think about how to correct for this. So the idea is to do some kind of alignment between the submaps so that we get a globally consistent map. And instead of doing this in the space of SDF, we can do it in the space of the features. So the features are, again, pretty useful for doing map alignment. So now the idea is something like this. I have the local keyframes here over time, and I have a local map. These blue squares are each of the local maps. And for example, at the coarse level, they have some features which correspond to each other, and I can try to align the maps in the feature space. And again, I can use this hierarchical structure. So aligning the coarse level features first, then the fine level features, and finally maybe the SDF itself. Existing work directly does this in the SDF space, which is slow, and it can be wrong. So we define a pairwise cost function here, which is essentially we have a distance between the features in map 1 and the features in map 2 projected back to map 1. So knowing the relative poses here, we can, and each feature has a 3D location, we can just convert back to the other frame and associate them and measure this pairwise cost. So we have, yeah, I mentioned this. So then we do a joint post-graph optimization in which the cost functions are essentially these alignments between the pairwise maps. So we can define a graph and where the submaps have this cost, as well as, again, there's some regularization term we can ignore. We can do this for the coarse or the fine level. So again, we do it in sequence. First optimize coarse level, then fine level, and finally, if things are still not good enough, we can also do SDF level reconstruction, where now the error is SDF prediction from map 1 versus SDF prediction from map 2. We can also optimize this loss. Okay, so showing what this might look like. So we have these different colored boxes representing the submaps. We do the feature association and the alignment, and after alignment, we expect to get a better map reconstruction. So there are some quantitative results which are a bit hard to read here. Essentially, these are some of the baseline methods that includes MIPS fusion is the first one in these plots here. The second one is Vox fusion ++ is another method which uses neuro-implicit features. The last one is ICP, and then the third one is ours. These bars are really hard to read, but the observation is that we can achieve more reliable, so the errors for our method scale better as you increase the error of the initial guess. So if you have the top is rotation error, the bottom is translation error. So as the initialization error is larger, our method performs better. At the lower initial errors, all the methods are quite similar. So some qualitative results as well. This is another data set called FastCamo. That's just what MISO is our method versus ISDF is the single MLP method. So these are some reconstructions of what these environments look like. We've done it on LiDAR as well. So you can do it RGBD, depth camera, or LiDAR. Our method is relatively agnostic to that. So this newer college data set is much larger scale. It's outdoor. And again, we can get pretty good reconstruction. And the main point is that optimization is fast as well. OK, so let's move on. So we talked about how to estimate sign distance function. As I mentioned, sign distance function also satisfies this nice property called the Autonomy equation. So the gradient of f, if we take the norm, this is equal to 1. So I'll talk about one more representation, which I'm excited about, is if you remember, we talked about NERF very briefly, that NERF takes position and viewing direction into account. So why aren't we capturing viewing direction in SDF? I think it's pretty useful for visibility on occlusion prediction. So we decided to also look into something called sign directional distance function, or SDDF. So the second D stands for direction. So the formulation is similar, but now we have viewing direction as another input. So we have 5 degrees of freedom as an input, 3D position, and 2 degrees of freedom for orientation. And again, we're predicting the distance to the surface in that direction, and positive or negative, again, is the same. And as I'll show you in a little bit, we have kind of a nice Autonomy equation for this case as well. The gradient projected onto the viewing direction is equal to -1. And this is what the SDDF looks like. So let's talk more about this. Why SDDF? So this is, again, definition of it one more time. Motivation. So, well, first, it's a different representation from what people have looked at. It's similar to NERF. We have position and viewing direction as an input, but that's different from SDF. And similar to SDF, we directly return distance. And that's unlike NERF. We don't need to do integration or sampling or ray tracing along the ray. We can predict distance right away. So one benefit of this is that it can predict distance very efficiently with a single neural network or whatever your function approximator is. So it should be much faster than NERF-like methods. And the second motivation for this is that it can be trained directly from LiDAR or depth data raw, so you don't need any pre or post processing. We are directly predicting distance. So this can be very useful for occlusion prediction. Okay, so let's talk more about this SDDF. So similar to SDF, we can think of a neural network to approximate this. So our training data is, for example, positions, views, and measured distances in these directions. So again, I can get this just from a point cloud or a depth image. And we just want to train a neural network which has parameters theta and predicts the distance. So it's just a standard regression problem. Inspired by work in SDF, we can also introduce one more feature, just like we saw earlier for the SDF work, which in the case of objects, for example, could represent object shape and things like that. I'll just show you some examples that are object level with this latent shape. SDDF also has some nice properties. I mentioned this Autonomy equation. So if we suppose we're very close to a point, so if I have a ray pointing in some direction, I hit a point on the surface. Let's call this point Q. And let's say the normal there at that point, the normal vector is n. We can show that locally SDDF behaves something like this. So from this, we can compute gradients. If the gradient exists, so gradient with respect to position looks like this. Gradient with respect to orientation or viewing direction looks like this. So why am I bringing these up? These SDDF functions have to satisfy these gradient properties. So if you want to learn them, you can encode those either in your cost function or even in your neural network by design to guarantee that what you're predicting is reasonable. So we can either have them as soft constraints in the loss function or as hard constraints in the network design. Okay, so let me show some examples of this SDDF. So for example, after training, so we trained this model on a collection of objects from ShapeNet. So you have a database of cars. We train this on a bunch of cars. And then at test time, if you're given a point cloud, like the one on the top from a new car you've never seen before, you can just call your model and predict the distance to this car from any viewpoint you want. And this can synthesize depth or point clouds for you. And you can assemble the point clouds into a complete model. And you can do this for different kinds of objects. We can show that similar to SDF neural networks, with SDDF, we can also do interpolation. So in this latent space of shapes, you can kind of change your latent code continuously. And you get, so for example, if I interpolate between two objects, two airplanes over here, in between, I get some airplanes that I've never seen. They don't exist. But just by changing that S feature, the network still synthesizes depth images or point clouds that look realistic. And here's an example of sofa. So you can think about kind of transforming one sofa into another. And in between the transformation, you still get reasonably looking sofas. Okay. So then we thought about, OK, what about SDDF for some simple shapes? So we can compute SDF for simple shapes. How about SDDF? And specifically, we looked at ellipsoids. They have been quite popular with Gaussian splatting. So let's look at an ellipsoid. Let's say I have a center C, orientation R, and radii R. I can define an ellipsoid like that. And we showed that you can compute the ellipsoid SDDF in closed form. I'll skip the equations, but you can get exactly the equation. So if your ray PV intersects the ellipsoid, we can get the SDDF exactly. Otherwise, the distance is infinity, or for this particular ellipsoid. And we have all the equations here. OK, so why do we want to do ellipsoid? Well, we first did SDDF for a single object, but then we wanted to do it scene level. So if I want to do reconstruction of a whole environment, how do we do that? So we developed a hybrid method in which we first, again, inspired by what I discussed in MISO, we first get a coarse reconstruction made up of ellipsoids only. Because for an ellipsoid, I can get SDDF in closed form, as I just said. And then we have a fine level neural network, which essentially predicts residuals or corrects the SDDF. So for each object, I kind of have a coarse ellipsoid first, and then I learn some residual around that to correct the error. So roughly it looks like this. So I start with a point cloud. I fit, we do something very simple, is initialize Gaussian splats or fit ellipsoids, for example, with k-means. So we have some initial guess of ellipsoids. This gives us an ellipsoid prior from the closed form computation I mentioned earlier. We can compute the SDDF f for these ellipsoids, as well as a couple of other variables. I is an indicator of whether the ray intersects this ellipsoid or not. And S is the sign, whether you're inside or not. And J here is the index of the ellipsoid you intersect. So if there's a bunch of ellipsoids, you want to predict which of them you will hit. From this, after we select a hitting ellipsoid, we compute local coordinates. So kind of which is the point that you hit with respect to this ellipsoid coordinate frame, and what is the viewing direction transformed to the ellipsoid local frame. From that, we extract latent features from the local point and viewing direction. And from those features, we train a residual network whose job is to predict the delta in the distance, the sign, and the indicator of intersection. So our final prediction then is the ellipsoid prior SDDF plus the delta f from the residual network. So essentially, each ellipsoid, you can think of it, has its own feature and predicts a little deformation. So if I model this bottle here with a single ellipsoid, obviously, I'll be wrong around here. So I want this residual to kind of correct the shape exactly. So what does this look like? Here's an example. So on the top is the ground truth. This is a simulated environment from my Gibson. This is the ground truth. So when we initialize our ellipsoid prior, it looks something like this. So pretty coarse, but reasonable prediction. We computed all the gradients can be computed in closed form for at least the ellipsoid case. So this is very fast to optimize. And a second thing is we guaranteed by design that the iconal equation, that equation that the gradient has to be -1 when you project it to the viewing direction, we can also guarantee this by construction. And this is what it looks like after the residual prediction. So a few more examples. Here's a different scene. So just ellipsoid approximation looks something like this. This is the SDDF prediction from the ellipsoids. Again, fairly coarse, but not bad. Then we introduce the residual. And that's the prediction we get. This is a comparison. This is the ground truth, top right. I don't know if you can see my pointer, actually. Maybe not. I didn't realize that, sorry. Yeah, ground truth is up there. And then here, bottom right, is a prediction by a Gaussian splatting method. So RAD-EGS is a method which trains Gaussian splats from depth images as opposed to RGB. So it's supposed to be more accurate in geometry prediction. Here's some more qualitative results. So again, we have a scene here from several different, actually these are from different data sets. One is from Replica, the other is from iGibson, the third is from ScanNet. We have the SDDF prediction, the Gaussian splat prediction. Note the Gaussian splat predictions are very good and very fast, but what we noticed is that they work only when there's both RGB and depth. When we tried this RAD-EGS without RGB, with only depth images, and the result is much worse. So if you don't include RGB, the Gaussian splat method doesn't work well. Then we have a NeRF-based method, and we have an SDF-based method. So this is what they look like qualitatively. So if you look carefully, I think SDF and SDDF are definitely better than the other options. NeRF can be good, but it's very, very slow. And sometimes it makes weird errors. We computed a bunch of error and timing questions. So I would say our method is, in the end, ends up being not as fast as the Gaussian splatting methods. So bottom table here, Gaussian splatting can be super fast. Ours is slower than Gaussian splatting, but faster than SDF and NERF methods. But on the accuracy front, our method, for example, with depth only or LiDAR only, which is this row, is as good as SDF methods. And it's a lot better than, for example, the Gaussian splat. If you don't have RGB, you get garbage out, essentially. OK, so what is this useful for? So we said you can do occlusion checking. So for example, we can very quickly define some cost function that I want to maximize my visibility, for example. And from this SDDF, I can predict what the visibility will be. And I can differentiate this cost and do things like find the view for a camera, which maximally views an area. Or if I have a whole room, I can choose a trajectory for the camera that maximally observes the space. So I can do things like guarding, for example, and exploration from this. So I have a differentiable way of doing that. And the motivation is to do this on a real robot as well. This is kind of an exploration example. It's actually using a slightly older model here. We were building it in 2D only. We're using Gaussian processes instead of a neural network. But we're looking to kind of implement this SDDF method on a real robot as well. You can also do things like, based on the occlusion prediction, you can, for example, track a mobile target, even if you don't always see it. But I will skip some of these details. If you're curious, we have an ICRA paper coming up on kind of this visibility trajectory optimization. I'm going to move on and talk about, OK, we have these SDF and SDDF maps. What do we use them for? So let's talk about planning and control a bit. So one thing that's nice about the SDF maps is that they give you distance to collision. So essentially, if I pick a point in my SDF map, it tells me gives me a distance or a radius of a circle, which is free of anything around me, which suggests that I don't have to do collision checking in this whole sphere. I can save on collision checking and motion planning algorithms in these whole regions. So this suggests thinking of something like an RRT algorithm in which I have spheres instead of points. And I don't have to do collision checking in any of these spheres. Second benefit is that my space is a union of these spheres, so I can easily think about trajectory optimization in which I have convex safety constraints. So we look at these extensions of RRT in which we're sampling bubbles. We call them bubbles. So we have a bubble roadmap, a rapidly exploring bubble graph, or a rapidly exploring bubble tree, or a expansive bubble graph. So these are all inspired by RRT variants. And again, the algorithm is pretty intuitive. So instead of points, we sample spheres. Given the SDF function, we can always look up we're assuming an SDF is given here, right? So we can always look up the radius. We find the nearest bubble in the current tree. We connect the bubbles and so on. So we can do, for example, so here's what this looks like. On the left, we have kind of covering the empty space with bubbles. And this also suggests some hierarchical planning approaches where first you can get a safe bubble path and then do trajectory optimization within the bubble cover. So you can, for example, standard ways would be you do some Bezier curve. You can make sure that the control points for your Bezier curve are contained within the bubbles, which will guarantee that the trajectory is inside. So as I mentioned, the main benefit is significant reduction in collision checking. And we can also guarantee safety within the bubbles. OK, but one problem with this, obviously, is how do you extend this to so if you have a car or a quadrotor robot, that's a single rigid body, that's fine. But what if you have an arm, right? Your configuration space is more complicated, or how do I transform the sign distance function into a configuration space? So this brings up the question of, can we define distance functions in configuration space, and what do they look like? So what I mean by this is we call this a robot configuration distance, or CDF. This was not from my group. It's actually a paper from last year at RSS, in which they say that if you have the regular SDF, you can then define a configuration space distance by looking at the distance to collision with a given point in the configuration space. So intuitively, right, if I have an arm, my workspace distance will be given in meters, is the distance between the robot body and a given point, while the configuration space distance is given as the distance from this configuration to a colliding configuration. So definition is something like find the configuration q prime such that the sign distance function at q prime is equal to 0. So at q prime, I'm touching the object, was the nearest configuration. OK, if we can build such a configuration distance function, then we can again do the bubble planning in configuration space now using the configuration space distance function. So we did that for an arm. This is, I think, a comparison between some of the RRT methods and our bubble CDF planner here on the bottom. Again, the main benefit of doing something like this is that you can save significantly in collision checking. So in these whole regions, you don't need to do collision checking. But how do you construct this CDF function? Again, we need to approximate it somehow. So we used a neural network again to approximate the CDF. So we're trying to train a model that looks like this. We have a function f, which takes as an input point and configuration q. And we need to find the nearest configuration, which is in contact with this point. So you can think about, well, there are several different ideas of how to collect a training set. But what we did, for example, is pick a bunch of points and then use the robot model to generate various configurations that are in collision with this point. So in this figure, for example, the purple star there is the point, and the gray, so this is just a two-link robot example. All the gray are example configurations that hit the point. So I have a bunch of hitting configurations. And then to train this, I can pick some test configuration, the blue one. And if I have this database of hitting configurations, I find the nearest one, and this gives me the distance. So that's how I generate training data. We repeat this many, many times. So given a robot, we sample many points. We do a lot of colliding configurations. We build this data set, and then we train a neural network to predict this configuration space distance function. So then from that, we can do the bubble planning again based on the configuration space distance. OK, then final thing I want to discuss is, OK, we know how to map. We can build a plan. So how do we do safe control in this space? So here I'm going to assume that we have some robot dynamics here. X dot is f of x plus gu. And we're interested in two questions. How do I follow the path that I planned with the bubble planner? And second is, how do I remain safe with respect to static and potentially dynamic obstacles? OK, so first let's translate those questions into something mathematical. We know that for following a nominal plan, that's essentially a stability question. So I can think of a Lyapunov function that defines the objective of tracking or stabilization. And the question of staying safe is related to safety question. So I can define a control barrier function in which kind of ensuring that the derivative here on the bottom of the safety of the barrier function h along the robot dynamics remains positive. So essentially, if I define my safe set as a set in which h is greater than or equal to 0, so that's an implicit definition of a safe set. If I can enforce the derivative to be positive, especially if I'm approaching the boundary, this will guarantee I remain inside the safe set. So these are ideas from Aaron Ames and collaborators, Paulo Taboada, and so on. So the main observation in this work is that both of these Lyapunov and barrier conditions are actually linear in the control input if you have a control-affine system. So you can use them in optimization as linear constraints. So in prior work, they showed that you can do quadratic programming, for example. You're minimizing the cost of deviation from some prior controller k here, subject to the stability and safety constraint. So yeah, the objective says follow the nominal controller. The first constraint says track a nominal plan. which, for example, can be from the bubble planner. And the last one says remain within the safety barrier, which can be the bubbles along the plot. Okay, so we can use the main idea is to use this configuration distance function, or CDF, as a control barrier function. So suppose we have an obstacle environment O, which is either time varying or not. And let's say we have the robot CDF. This was the FC function, right? So I can define a control barrier function, which is essentially for all the points on the boundary of my obstacle set. I want the CDF to be greater than or equal to 0, which means that I remain safe. In practice, I cannot observe the environment directly, and I have errors in estimating the CDF as well. So we really had to think about how to make this robust to errors. So in practice, we probably just have a point cloud observation of the environment. So instead of O, I have some point cloud P here, so I compute the min over all the points I get in my point cloud. So I have some error from this. And second, I use this neural network approximation of the CDF, which again introduces some error. So this kind of brings up the questions of how do I deal with these sources of uncertainty. So localization and measurement error essentially create variations in P. I query the CDF at the wrong point, and variations in robot shape or uncertainty from training the CDF function gives me some variations in the parameters of the neural network. So our main idea here was to look at distributionally robust version of the CBF constraint. So instead of minimizing the CDF constraint directly, we're interested in minimizing the probability over this variable of variation. As I mentioned, the variation in our case is induced by uncertainty in the locations for the points or in the error in the neural network from the training. So the errors usually come in your estimate of h and its derivatives with respect to space or time, if you have a temporal dimension as well. So I'm going to define this variable c, and I treat it as a random variable. It's something I can measure based on either the neural network, CDF, or the point cloud, but it's something that has error. Okay, so instead of checking the safety constraint directly, I'm going to think about what is the distribution of zeta and how am I robust to this distribution. Well, as you can guess, we don't know the distribution of zeta, but we can get samples from it. So the point cloud or the CDF essentially gives me different samples for the zeta. So we're interested in kind of enforcing this constraint using samples rather than knowing the exact distribution. And this is exactly what distributionally robust optimization thinks about. I think I'll skip some of the details because we don't have too much time. But let me give a quick overview of what the idea is. So if you have this probabilistic constraint now, so I had the safety constraint before, which is, let's say, just a control barrier function. But now I have this zeta parameter here, which gives me the uncertainty. And I want a chance or probabilistic constraint over this. So how do we enforce this constraint? Well, there are several problems. So first, this constraint might not be convex. And second, I might not even know what P is. So first, to make it convex, there are some ideas from Nemirovsky and Shapiro. You can use a conditional value at risk to get a convex under approximation of this. So skipping some of the details, there's something called conditional value at risk, which kind of looks at the expectation of the random variable in the worst case. So in the epsilon worst case of scenarios, what is the expectation of the random variable? So we can reformulate this into a CVAR constraint. What's the main reason for doing that? Well, you can show that the CVAR constraint implies the chance constraint, but it's convex. So there exists a convex formulation of this. So you kind of are a little bit more conservative, but you can get a convex constraint. Again, so far we assume we know the distribution of P. I'll skip a little bit. But what if the distribution is not known? Then we can assume we can get samples, which is the scenario we mentioned. And we build a set of possible distributions P that are near to the empirical distribution. So P hat here is an empirical distribution I can build from samples. And I consider a ball around this P of all possible distributions. And I want to enforce the constraint for all of these distributions. So usually we use some distance metric, and in the probability space, in this case is Wasserstein. So usually distributionally robust optimization uses a Wasserstein metric. again, skipping some details, specifically for one Wasserstein distance under some assumptions here. Maybe the main one is that your uncertainty shows up in a convex way in the safety constraint. You can get a reformulation of the CVAR constraint into something that is convex. So essentially, you can get a convex constraint that is built only from samples, and that implies the CVAR, which in turn implies the probabilistic constraint. So I know I skipped a lot here in the end, but we get something like, so this is our original safety problem on the left. We wanted to solve. That's distributionally robust. We do this transformation. This gives us the convex reformulation, which is safe. How do we get these samples? In practice, we can sample different robot poses and different distance measurements and collect all of these samples and enforce that. All right, so let's look at some examples. So here's putting everything together. On the left is just autonomous navigation in some environment. On the right, you see kind of an obstacle that's time varying and dynamic. So here we get the measurements, and we use the CBF to enforce the constraint. We can do things like variations in shape. So we use the same approach, but different robot shapes. You can still stay safe. We can deal with pedestrians or kind of unknown obstacles, remain safe with respect to those. And we can apply this to an arm as well. So here's an example with the CDF where the arm has some goal it needs to get to, but along the way, there's a moving obstacle disturbance that's just messing with the arm. Okay, I think let's conclude because I was a bit slow. So in what we talked about is that learned environment representations can give you a variety of information, geometric, photometric, and semantic, and I think those are useful. Distance functions and directional distance functions are particularly useful for safety and visibility specifications. And in future work, I think it's important to think about these spatiotemporal environment representations and how to encode more features into them and how they relate to motion planning and task planning more generally. And I also like the modular view of robotics where we have an environment model, a robot model, and a task model. So I think there's a lot of promise there. And some acknowledgements to my students who helped or did a lot of the work, and funding information as well. And I'm happy to take questions.
Questions?
Yes, go ahead.
So in the chance-constrained planning stuff at the end, you have a big, long chain of implications that get more and more conservative. So in practice, does it like not drive through doorways?
Yeah, good question. Yes, definitely things get more and more conservative. Let's see. Yeah, there were kind of from here to here and from here to here. So there are kind of two implications which get more and more conservative. Yeah, I think in the end, it depends on the variation in your samples. So if your error is small, so essentially if your samples are always the same, then all of these implications will be tight. So as your sensor gets more and more, or your uncertainty gets larger and larger, this gets more and more conservative. So potentially there are different ways of reformulating things. One of these was specifically to get convexity, and the other one was kind of more inspired by the uncertainty. So those are the two reasons. This one implication is from convexity, the other one is from uncertainty in the sensor. So I would say the first one, maybe there are ways around it. There are other convexification. Even this one, there's conformal prediction is another way in which you can get robustness with respect to samples. So there could be tighter ways of getting this. One thing that's nice is that we're not using any information about the distribution here. So maybe that's where the conservativeness comes from as well, but we don't need to kind of know the statistics of these samples. So if you do know that, again, things can be tighter probably. Yes?
I have a technical question and maybe a philosophical question. So technically, what do you see as the connection or relationship between some of these sign distance methods or the methods that you're starting to push towards, like, you know, the robot arms and beyond, like a point system, and like reachability?
Okay, yeah, what's the connection between SDF and reachability? I think it's a great question. So I skipped some stuff because I thought I didn't have time for. But one nice observation, maybe I won't answer your question exactly, but let me give you one nice observation. So we looked at just optimal control formulation. If you have a fully actuated system, so x dot equals u, and your cost function is only state dependent, not control. In that case, the Hamilton-Jacobi-Bellman PDE simplifies into something that looks like an Eikonel equation. So essentially, you have cost function to value is an Eikonel equation. So I think I can imagine a chain. Maybe that's not safety yet, but I imagine a chain where you go from point cloud measurements into SDF by enforcing Eikonel, and then from SDF to value function, again by enforcing Eikonel. And I imagine for safety, there could be similar ideas.
So that's why I'm asking it, because typically, like, the reachability procedure is first you give me a signed distance function to represent the failure, and then I do dynamic programming to get a reasoning about the dynamics, like the coupling between that constraint and not. And if the dynamical system is trivial enough, like it's, like, you know, like x dot equals u, then the failure set and the value function are the same, because you can instantaneously move and nothing matters. And the reason why I think this connection could be cool is because if you're developing some techniques, then maybe we could start like porting them over, like computationally, if they ultimately are starting to look like they're trying to regress kind of the same thing.
Yeah, I'll mention one more thing, which, let's see if I can find it, which we did, but I didn't mention here. Yeah, so this is a little bit of what I was saying. So you have the, with simple dynamics, you get value function is essentially an Eikonel equation over the cost. And you can think of this as a neural operator. So for example, your cost, this Eikonel equation takes a function and produces a new function. So you have cost function, give me value function. So instead of training neural networks, I can think about training neural operators now, which directly map from cost functions into value functions. We did some very preliminary work on this, where so there's a lot of going on in the neural operator field. So we showed that you can design a network which, this is essentially a neural operator. There's a lifting operation, which extracts features. There's a number of Fourier layers, which kind of get features in the frequency domain to make things resolution independent. Usually they model the map in a grid, and then there's a projection layer. So essentially you can map something like, given an SDF, you can directly predict value function, but it's still a relatively simple setting. You need like these trivial dynamics and stuff like that. But you can learn to predict that instead of computing it.
And then my philosophical question for you is, so, you know, the work on, for example, map construction is very, very beautiful. But you might be spending a lot of time doing reconstruction in parts of the environment that don't actually matter. Have you thought about co-optimizing the task that the robot is ultimately going to do with this map and the resolution or fidelity of how you're actually constructing your representation of the environment?
Yeah, that's a great question. I would say for now we haven't. We've just built maps, but at least we've started to think about these hierarchical representations, as I discussed earlier. So you can definitely imagine that for some parts of the environment, you only keep your coarse level features and you don't get into the details. And for other parts, this also has to do with the resolution of the feature grid. Yeah, you can choose the resolution adaptively, potentially. But no, we haven't explored too much of this. I think it's a good question.
Maybe like harping on that a little bit, and we were talking earlier about this kind of thing, like I see a lot of this work is meant for like, you know, kind of mapping, and generally it's for like collision avoidance.
Yeah.
And I think more and more we're interested in like actually interacting with the world and touching it. And so I feel like there's a whole bunch of new problems that come up when you care about this stuff for contact planning and for manipulation planning, and like kind of just general thoughts on how this sort of thing, you know, maybe will evolve in that direction, or where you see problems in that
great question. Yeah, and I admit I come from a mobile robot navigation point of view, and mainly done mapping for navigation in the past. So I'm new to manipulation, but I think that's where the cool problems are, and I find this really interesting. So what I can say is that, well, first, maybe starting object level, right? A lot of the things I mentioned can be done object level, and they for sure give a lot of information. So let's see if I can go back. So for example, with this SDDF stuff, I can predict kind of novel views, distances, point clouds, mesh, and stuff like that for objects. So I'm sure that this is useful for manipulation. I don't have an exact answer, but what I'm interested in trying is to have these neural features as an input to reinforcement learning as opposed to image features. So in a lot of manipulation, people do it like you have images, you extract features, and you train RL to grasp an object or to open a door. I think just basing it off of the 3D information would give you better information, I think, but I don't have proof yet.
We're playing with some of this now, and I can tell you like one of the big issues is just geometric uncertainty. Like grasping is terrible. Like you like can't do stuff. And so I'm particularly interested in some of the views on like robustness and like managing uncertainty in some of these formulations and how that might inform like a planner.
Yeah, I think for uncertainty quantification, we've done it in simple cases, but when we get to this map level, it's like if you want like a really large environment representation, the main challenge I see is that there's too many dimensions and too many features. So I think it's difficult. I don't have a good answer. Yeah.
Any other questions?
Yeah, maybe I have a super quick question. Like, maybe it's like a follow up on Zach's question. So maybe I missed the detail. Like when we turn the SDF to manipulation, like configure space. How do you make sure it's still bubble? It's probably still convex. I imagine for like if you go do beyond like 2 dot like 7 dot arm, you need to handle like very non-trivial DH matrix stuff like that, right? How do you make sure that this is still a bubble?
Yeah, good question. So I think intuitively, let me see if I can explain it. So intuitively in the workspace, they're bubbles. If you transform them through your Jacobian, they will get more ellipsoidal looking or might not be exactly bubbles. But if you change the metric in this space, you can deform stuff so they look like bubbles again.
They may not be connected, right? Because you have
yes, the space is not connected. Yeah, they're a union of bubbles, right? So we're locally for a given configuration, we're just trying to find. So let's say I have my whole world is a bottle, okay, and I have my arm. What we're measuring is kind of what is and let's say I only have one joint here. So what we're measuring is the distance in radians here to collision. So this gives me the distance. So I can define a bubble now in the radiance space that tells me in this region, right, I'm safe. So I don't need to do collision checking anywhere here. I only need to do over here. And then you cover the whole space with these bubbles.
You use like to approximate a non-convex region.
Yes, exactly. For sure, they're an under-approximation of the true reachable space. But we can do union of that. Exactly.
Do you know how like loose that is?
I'd say pretty loose, yeah. Especially with the learning, it's quite loose. But we can, with the sampling, right, we can do many of them. Yeah, I don't think the real reachable sets, they're nothing like bubbles at all. Yeah, so I think it's pretty coarse, yeah. But I mean, if you have a non-zero radius, you're already doing better than just RT. So to me, that's the point. I like bubbles with slightly large radius, but they're still bad approximation, yeah.
Awesome. Okay, let's thank our speaker one more time.